me guys, I'm Eliza, and today we're going to dive into the world of limits. Are you ready to learn in a fun and adventurous way? Let's get started. But first, we need a map. Say map, say map, and say map.
If there's a limit you must know, I'm the guide to help you show. I'm the map. I'm the map, I'm the map. If there's a value to get near, I can help it crystal clear. I'm the map. I'm the map, 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 I'm the map.
Here's the map. Can you tell me what our first topic is? Correcto, defining limits. Do you have any idea what a limit is? Imagine you're at a milk tea shop. The counter is right there, but there's a long line. As you move forward, you're getting closer and closer to ordering your drink, but technically, you're not there yet. Oh, like when you get closer and closer to losing your patience? Limits? Like the limits of your patience? Just like that. In math, a limit tells us what a function is approaching as we get closer and closer to a number. Just like you, approaching the front of the line. But wait, do we always reach the value we're approaching? Sometimes we do, and sometimes we don't. Now, let us take limit of x plus 2 as x approaches to 2 as an example. And then let's get over here. We have our left and our right hand columns. At this part of the left hand, we will put the approaching value of the limit. Over here, we have a number line. It is to determine the values of the left and the right hand limit. We will put 1 to the x value of the left hand and then go back to here and put 3 to the x value of the right hand. The left hand limit means we are approaching to 2 from the left, which means choosing numbers that are slightly less than 2. We pick values that gradually get closer to 2, such as 1.5, 1.9, 1.99, 1.999. For the right hand limit, we choose numbers that are slightly greater than 2, which are 3, 2.5, 2.1, 2.01, and 2.001. Now, we will solve for the f of x part of the left and the right hand limit. To do that, we have to take the approaching value and add it to 2. So for the left hand, 1 plus 2, 1.5 plus 2, 1.9 plus 2, 1.99 plus 2, and 1.999 plus 2. The answers are 3, 3.5, 3.9, 3.99, and 3.999. Let's now input this in the f of x column. Now that we have the values of both the left and right hand limit, let's now make a graph. Here's the final graph and the plotted left and right hand limit approaching 2. Bit of teamwork. Now, my friend Kyla will take over to explain more about limits as she will use it for our next topic. Vamonos!
Hola explorers, and thank you Eliza. Now that we defined what limits are, let us now proceed to our next destination. But what do we need first? That's right, our map.
If there's there's a function we must solve, I'll show the way to get involved. I'm the map. I'm the map, I'm the map. If there's a pattern to apply, I hope you find the reason why. I'm the map. I'm the map, 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 I'm the map.
So amigos, what's our next topic? Correcto, evaluating limits. That sounds fun but maybe a little tricky to understand. But don't worry, I got you. But before we start, let me ask you all a question. Have you ever ridden a roller coaster before? It's both exciting and terrifying, right? But think about it.
Before you actually drop, the coaster gets closer and closer to the big hill, right? You slowly climb up, and then you just know what's about to happen. And then boom, the drop. But what if the coaster just gets closer and closer to the edge, but never actually drop? Scary, huh? But here's the thing. In math, we don't actually need to reach a value. We just need to know what we are approaching to. Just like you know that the roller coaster will drop even if you pause right before the fall. And that's it, amigos. Now that you have an idea what evaluating limit is, let us now proceed to our actual discussion.
In evaluating limits, we have some important tools that will help us. The limit laws, which will help us break down complex limits into simpler parts, making them easier to evaluate. Let's move on to our first one.
Here we have our first theorem, which states that for any real number c, limit x is equal to c as x approaches to any real number c. Here is our example. In this equation, we will use the theorem 1.1, which will be limit x will be equal to the value as the value of x is approaching 2, which is 8. And that is our final answer. And as simple as that, we are done with our theorem 1.1. And let us proceed to our theorem 1.2, which states that for any constant k and real number c, limit k is equal to k as x approaches to any real number c. Let's look at this example. In this given equation, we will use the theorem 1.2. Our constant here is the number 3 and our real number c is the 2. So according to the theorem, the value of our limit 3 as x approaches to 2 is just simply equal to the value of the constant k of our limit, which is 3. And that is our final answer. Now that we are done with our theorem 1.2, let us now proceed to our theorem 1.3. Under this theorem, we have 4 limit laws. Let's tackle first the first law, which is the constant multiple law, which states that limit k times function x as x approaches to c will be equal to k times limit function x as x approaches to c. We just simply get the constant k outside the limit and copy the limit. And let us have this example. So in this equation, we'll just simply apply the constant multiple law, and that would be taking out the constant outside the limit. 5 times limit x cubed, just copy that, the variable, and don't forget the value as the x is approaching 2. With this, we just copy the constant 5, and here we could apply the theorem 1.2, which will copy the value as the x is approaching 2, and don't forget the power, which is cube, and that would be 5 times 27, and 5 times 27 is 135. And that is your final answer. Alright, now that we are done with our constant multiple law, let us proceed to our second one, which is the sum and difference law. In this law, limit f of x plus minus g of x is as x approaches to any real number c. In this, we just simply distribute each limit into each term. And that would be limit f of x as x approaches to c plus minus limit g of x as x approaches to c. And here we have an example. So in this given equation, we'll just simply use the sum and difference law. And that would be distributing each limit into each term. And that would be limit of 3x is x, and then just copy the operation and limit 1, and don't forget the value as the x is approaching 2. So with this, in the first term, we could apply the law that we discussed earlier, which is the constant multiple law, because it has a constant k and a variable x. And we will take that constant outside the limit, and that will be 3 times limit x as the x is approaching to -4 plus, and with this we just copy limit 1 as x is approaching to -4. Next step is to copy the constant 3, change the value of the limit x into the value of the x is approaching to, which is -4. Copy the operation, and that would just be 1 because it has no variable. So just copy the 1. And the final answer is -11. And here you have your final answer. So explorers, we are done with our 2 limit laws, and let us proceed to our product law. In product law, we just simply distribute the limit into each term, which will give us limit f of x as x is approaching to any real number c times limit g of x as x is approaching to c. And let's refer to this example. We apply the product law, and it will give us limit x plus 6 times limit x minus 5. And x is approaching to +2. Again, you just simply distribute the limit into each term. And the next step is to change the variable x into the value of the x is approaching 2, which is 2. And copy the constant 6. And same with the second term. 2 plus 6 is 8 times 2 minus 5 is -3. And that would be 8 times -3 is -24. That gives you your answer. Alright, we are now done with our product law, and we are down to our last limit law, which is the quotient law. In this law, we simply distribute the limit into each term, both in the denominator and the numerator. And that would be limit f of x as x approaches to c over limit g of x as x approaches to c. And here we have the last example. We just simply apply the quotient law, to which we distribute the limit into the both numerator and denominator. That would be limit 3x squared minus 5x plus 4 as x approaches to 2 over limit x cubed plus 2 as x is approaching to +2. The next step would be distributing the limit into each term, which is discussed earlier in the sum and difference law. You just distribute the limit into each term, both in the denominator and the numerator. And that would give us limit 3x x approaching to 2 minus limit 5x x is approaching to 2 plus limit 4x is approaching to 2 over limit x cubed x is approaching to 2 plus limit 2 x is approaching to 2. After that, we evaluate each term. In this first term, we could use the constant multiple law, taking out the constant and then copy the limit. Same here with the second term, minus 5 limit x as x approaches to 2. In this case, we just copy the term. And for the denominator, we just copy both terms. And the next step is evaluating limits. And that would give us 3 times 2 squared minus 5 times 2 plus 4 over 2 cubed plus 4. In this case, we just apply the basic math. That would be 12 minus 10 plus 4 over 8 plus 4. And that is equal to 6 over 12, or the simplified term is 1/2. That is your answer.
Thank you, Kyla. You've done an amazing job. Now that we've explored the basic of limits, let's take things up a notch and dive into the next topic. But first, we need our trusty map, don't we?
If there's a function we must solve, I show the way to get involved. I'm the map. I'm the map, I'm the map. If there's a method to apply, I hope you find the reason why. I'm the map. I'm the map, 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 I'm the map.
Before we get to the actual calculations, let's imagine something fun, like sharing a pizza with friends. Let's say we have a giant pizza and 4 really hungry friends. If we keep cutting the pizza into more and more slices, what happens to the size of each slice? Correcto, amigos! It gets smaller and smaller. The more slices we make, the closer each slice gets to 0, but it never actually disappears. That's like limits. They help us understand values that get super close to something without necessarily reaching it. We have a bunch of techniques in calculating limits. Can you name one? Great job! We have direct substitution, factoring, rationalizing, and L'Hopital rule. But today, we're only going to focus on substituting and factoring just to make our life a little easier. Trust me, these two techniques is really helpful and will get us through most of the problems smoothly. But first, tell me, where is the equation? That's right, it's right behind me. Alright, let's go through the first one. So we have here p of x equals 2 over 3 x cubed minus 5x plus 4, and our x is approaching to 3. Do you know what technique should we use in this equation? Correcto! It's substituting. We are going to substitute 3 to all x's. After plugging in x equals 3 directly into the function, we calculate 3 cubed. Three cubed should equal to 27 minus 5 times 3 equals to 15. Then plus 4. After multiplying 2 over 3 to 27, the answer should be 18, minus by 15, and plus 4. Now, can you tell me what the answer is? If you said 7, bravo! You got it right, my friend! Now, how about if we can't apply direct substituting technique? What should we do? You're so smart, my friend. It is factoring. We can apply factoring when our direct substitution leads to an indeterminate form like 0 over 0, like this one. As you can see, limit x squared plus 5x minus 6 over x squared plus 2x minus 3, and x is approaching 3. And now, we need two numbers that multiply to negative 6 and add to 5. Those numbers are 6 and negative 1, so we factor it. And here in our denominator, we need two numbers that multiply to negative 3 and add to 2. The numbers are 3 and negative 1. And now, we rewrite our expression, and this is it. Notice that both the numerator and denominator have x minus 1, so we cancel it out. And now, let's substitute x equals 3 into the simplified expression. And this is our final answer. And that, my friends, how we factor out and substituting limits. Alright friends, now that we've tackled substituting and factoring, it's time to pass it to my amazing friend, Hyacinth. They're going to guide us to the next part of our adventure. Take it away, Hyacinth.
Thank you, Jules. I'm so excited to dive into our next topic. But what do we need first? Correcto, our trusty map.
If a function's nice in it and doesn't skip or miss a bit, I'm the map. I'm the map, I'm the map. If one punch low and one punch high, a value in between must lie. I'm the map. I'm the map, 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 I'm the map.
Continuity. So what exactly is continuity? Good question. Imagine you're pouring a glass of water. You tilt the pitcher and the water flows smoothly into the glass. No sudden stops, no breaks. That is continuity. But what if the water suddenly stopped mid-air? Or there was a gap where no water flowed? That wouldn't make sense, right? The flow should be smooth and unbroken, just like a continuous function in math. Okay, enough with that water. Let's define continuity. Can you say continuity? Excelento! Continuity function is said to be continuous at a point if you can draw its graph without lifting your pen. In other words, there's no sudden jumps, holes, or breaks in the function. Now, let's look at this function. F of x is equals to 2x plus 3 at x equals to 1. Is this function continuous at x equals to 1? Let's find out if all three conditions are met. The first condition is it defined at x equals 1? Yes, since f of 1 is equals to 2 times 1 plus 3 is equals to 5. Now, the second condition is, does the limit exist as x approaches to 1? Yes, since f of x is equals to 2x plus 3 is a linear function, the limit as x approaches to 1 is just 5. So hence, the limit exists. The third condition is, does the value of the function equal the limit at x equals to 1? Yes, since f of 1 is equals to 5, and the limit as x approaches to 1 is also 5. Since all three conditions are met, is the function continuous or not? Yes. It is continuous at x equals to 1. Good job, guys! Now that we've explored the basics of continuity, I'm going to pass the map to my trusted friends who will take us through the world of theorem. Take it away, Daphne and Missy.
Thank you, Hyacinth. I hope you all enjoyed learning about continuity. Now, let's take a step further and dive into our new topic together with my friend here, Missy.
Hola amigos, are you excited to learn our new topic? But what's our new topic?
We need our trusty friend, the map.
If a function's nice in it and doesn't skip or miss a bit, I'm the map. I'm the map, I'm the map. If one point slow and one point high, a value in between must lie. I'm the map. I'm the map, 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 I'm the map.
So, amigos, what's our new topic?
That's right!
It's intermediate value theorem. So, what is intermediate value theorem? Let me ask you a question. Have you ever climbed a staircase step by step? Of course you did. You can't skip any steps, right? You must pass through every height in between. Well, functions work the same way if they are continuous.
Oh, so if we start at one point and at another, we must go through all the values in between?
Correcto, Missy. That's the intermediate value theorem. It tells us that if we have a continuous function, meaning there are no jumps or gaps.
Wow! So it must hit every number between and at least once. But how does this help us, Daphne?
Great question, Missy. We can use the intermediate value theorem to prove that an equation has a solution in a certain range. Let me show you how it works with an example. Can you tell me where the equation is? That's right. It's right there. We have f of x equals to x squared with the intervals of -4 and 2. And our given w is 9. First, we will substitute our f of a and b using the intervals. F of a is equals to x squared, so f of -4, our interval, equals to -4 squared equals to positive 16. To our f of b equals to x squared from our equation, f of 2 equals to our interval, square equals to positive 4. Now we prove our intermediate value theorem by our f of a and f of b are not equal. Now, let's move on to our w. The product of our f of b is 4, and our given w is 9, and the product of our f of a is 16. This proves that our product is right, since 9 is between 4 and 16. Here we have our f of c equals to -4, our interval lesser equal than c, and c is lesser than equal to interval 2. F of c is always equals to 0, equals x squared. We bring down 0, we have square root of 0 equals to square root of x squared. Cancel out, which leaves us square root of 0 is equals to x. Going up to our f of c is equals to 9. The given, our w and our f of c is equals to x squared. Using these formulas, x square root of 9 equals to square root of x squared. Cancel out, we have x equals to plus and minus 3. We have x plus 3 and x minus 3. We will be using our intervals -4 lesser equals than positive 3, 3 lesser equals than 2, -4 lesser equals than -3, lesser equals than 2. We will be using this to graph our c, because 3 is greater than 2. Now, we go to our graph. We have our point f of a is negative 4. Our interval and 16. Point f of b, our interval 2 and 4. Here we have our negative 3 and our 9. And we have c as our right angle. And now, we curve our graph.
That's all, amigos! I hope you all had fun learning the intermediate value theorem with us.
But guess what? We're not done yet.
Let's have our friend Jacob to take over and introduce us to our last exciting topic. Take it away, Jacob!
Thanks, Daphne and Missy. That was an amazing journey through the world of intermediate value theorem. Now, let's head over to our next topic. But what do we need first? Correcto, the map.
When a function starts to shift, slopes will tell us how it drifts. I'm the map. I'm the map, I'm the map. Tangent line will help explain how a graph will rise or wane. I'm the map. I'm the map, 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 I'm the map.
So what is our last topic? Derivatives. Amigos, what exactly is a derivative? Let me ask you all a question. Have you ever been in a car speeding down the road and wondered how fast you were going at a specific moment? Well, the derivative is like a speedometer that tells us how fast something is changing at any given point. But hold on, today I'm just going to focus on introducing some important concepts which will help us understand derivatives more clearly. Can you tell me what this is? Correcto, it's the tangent and secant line. A secant line is a straight line that passes through two points on a curve. In this case, the curve is represented by a function, and the 2 points where the secant line intersects the curve are. These points correspond to two different x values, meaning they are not the same point. So, applying the slope formula, the slope of the secant line is. The second line helps us calculate the average rate of change of the function between how many points? That's right, 2 points. For the tangent line, we take the idea of the second line and refine it further. Tangent line is a straight line that just touches the curve at exactly 1 point without crossing it. Imagine, we're having a curve and we're looking at a specific point on this curve. But how do we find the equation of this tangent line? That's right, we need the slope formula. This means we take the second line slope and shrink the gap between the 2 points, making them closer and closer until they become the same point. This is what we call taking a limit, and it gives us the derivative or the exact slope of the curve at a single point. Alright everyone, that's all for introduction of derivatives, introducing the slope formulas, the second line, and the tangent line, as well as the points. And this concludes our journey.
Wow, what a journey today, huh? From limits, continuity, and derivatives, we've covered so much. Gracias to all of you for joining us. It's like we've unlocked the secrets of math step by step.
And don't forget the power of continuity and how it helps us to understand functions. We couldn't have done it all without you.
Absolutely. I love exploring limits with all of you. Big shout Math for guiding us through it all.
And remember, math is always an adventure. Big thanks to you, our amazing audience.
And remember, friends, whether it is limits or derivatives, it's all about understanding the journey, not just the destination. Big thanks to our trusty map for guiding us the way.
Well said, Hyzen. All right, math adventurers. Until next time. Wait, a big thanks to the map for always being there when you need it most.
Hola!
Intermediate value theorem.
Niggas steady jocking 'cause they know I'm the truth. And I get it from my mammy, but I made bust down. These hoes can't stand me. You know the girl me, pussy poppin' with your ear. Chanel and pearls, that's the trench that it takes. The girl.